students. So today we will discuss about the materials used in semiconductors, used via semiconductors, and on which the whole electronic industry is based. Now, if we talk about elemental semiconductors, and in particular, we know all about the element silicon, which has been useful for development of electronics. There are some drawbacks associated with silicon, which you all know. The fundamental drawback is silicon is indirect bandgap material. Means the minimum of the conduction band and the maximum of the valence band, they are not at the same K value. So there is a phonon assistance required for the electron to travel between these 2 points. So this is what is known as indirectness associated with the semiconductor with silicon, which is not found in case of gallium arsenide or direct bandgap semiconductors. They have their maxima of the valence band and minimum of the conduction band at the same K values, so electron transfer and photon emission is much easier in this case. So these are direct bandgap and this is indirect. So this is the fundamental drawback of silicon. Now we are also into something called compound semiconductor, which has been offered for many desired properties. Like in this case, if we take about this property of indirectness, so we have seen that the compound semiconductor, the gallium arsenide, can solve this property of indirectness. And these are basically, look into the periodic table. These are basically 3, 5, 2, 6, 4, 6, and 4 compounds. Now, for the purpose for indirectness, as we have said, like gallium arsenide is a 3, 5 compound. That is, it is taken from the 3rd group, and this is taken from the 5th group. So this is a 3, 5. Similarly, we can have indium phosphide, which is also a 3, 5 compound. Now, the average, now let us represent the compound semiconductors as in a different way. Look at this bandgap. The compound semiconductor is represented as A3 and say B5 or C2 and D6. And these compound semiconductors, they have the same average number of valence electrons per atom as in silicon. So the properties have same average number of valence electron per atom as in silicon. That is 4. And for silicon, it is 4. And if you look into these compounds, it is observe is that the sum of outer electrons is 8. So since we have two elements, the average becomes 4. 8 by 2, this is also 4. And if we look into this compound which we have recently discussed, that is indium phosphide. Sorry, not indium phosphide. Let's take this compound. Indium antimonide. This was the first 3-4 compound. This is basically 3-5 compound. This was the first 3-5 compound to be discovered, and it was discovered in 1950. And the particular features of this compound that attracted interest were the ease with which it could be synthesized. So, ease of synthesis, and then the electron mobility and ionic component in the crystal bond. You know that there are two types of components. One is a covalent component, one is an ionic component in the crystal bonding. So it has a very high ionic bonding. And these properties are still of immediate interest, and they are used due to these properties. That epitaxial growth of that is crystal upon crystal growth. Epitaxial growth is also searched on all these compounds. Another property that this compound they have got a low band gap, that is 0.17 electron volt, and due to this they have been used for development of far infrared detector technology. The other compound semiconductor that is of very much importance is gallium arsenide. Now, there were two important events. Like the first was invention of semiconductor laser. And discovery of something called gun effect, which I will discuss in another video. Due to these two inventions, the importance of gallium arsenide increased. Now, gallium arsenide has a band gap of 1.43 electron volt. And similar to that, another compound which is very much similar to this gallium arsenide, that is indium phosphide. It has a band gap of close to gallium arsenide, that is electron volt. The next, in terms of order of importance, the next compound semiconductor is gallium phosphide, which has a band gap of about 2.1 electron volt. The importance of this is due to, from the band gap, if you calculate, you know that Ag is equal to Hc by lambda. So the lambda here, due to this high band gap, the lambda comes into the visible part of the spectrum. Due to this property, the gallium phosphide become important, and they are mainly used in formation of LEDs, light emitting diodes. Now, one important thing is that the band gap associated with gallium arsenide is not purely direct, but there are some indirect elements associated with this gallium phosphide. It is not as big as silicon, but there are some indirectness, and by certain doping techniques we overcome that. And by doping, what we do, we improve the radiative efficiency of the material. Now these compound semiconductors that we discussed, like gallium arsenide, indium phosphide, they have higher electron mobilities and velocities. You compare them with silicon and germanium, compare them, then these materials, they possess higher electron mobilities are high, and electron velocity is also high, and due to this they are specifically used in making high-speed electronic devices. Now, whatever compounds that we have discussed, these are all binary compounds consisting of two elements. Now, another feature in semiconductor technology is these binary compounds can be combined or allied to form ternary or quaternary compounds. So they can be allied, should say combined, or allied to form ternary or even quaternary. compounds. Ternary means there are 3 elements. Quaternary means there are 4 elements in the compound semiconductor. Or they can also form something called mixed crystal. Now, when we are choosing different binary compounds, say we are choosing 2 binary compounds. So, two binary compounds will have different band gaps. So, different binary compounds will have a different band gap. So the final product after combining these different binary compounds will have varying emission energies for light sources. So varying emission energies for light sources. However, if we do a little bit of alloying, it helps it leads to a possible variation of continuous and monotonic variation of band gap. So we would have a control over the band gap, and it will also be helpful in making the different devices. So control can be done with the help of alloying. Now, another important aspect in making this ternary and quaternary compound is the formation of something called heterojunction. And these are essential for the design of high performance devices. Let's take an example. For example, we take a ternary compound like take aluminium, X, gallium 1 minus X, arsenic, where the value of X lies between 0 and 1. This ternary compound depends on the mole fraction X. So this is basically the mole fraction. So its property will depend upon this mole fraction X. Now, so in this clipping we can see that there is a combination of gallium and arsenide, which will give you, if you take X is equal to 0, automatically there won't be any aluminum. So only we are left with gallium and arsenide. So automatically the band gap will be 1.43 electron volt, as in the case of pure gallium arsenide. And if we take X is equal to 1, then of course you can see that there is no gallium, so the compound that will be formed is only aluminum arsenide, and in this case the band gap will be 2.1 electron volt. So you can see that by varying this mole fraction, how we can tune the band gap and we can use it for a particular use. Now, apart from this values, there are other properties like optical properties of the mixed crystals. We also change in alloying, and they are actually exploited in design of electronic and optoelectronic devices. Now, this material is the most studied material. We consider gallium arsenide and indium phosphide, and other important ternary and quaternary compounds that are looked into are, say, gallium arsenide 1 minus X, PX. This is one of the ternary compounds, highly sustained. Then we can have indium 1 minus X, gallium X, P. Then we can have indium X, gallium X, aluminium 1 minus X minus Y, no, sorry, different color here. It's indium X, gallium Y, aluminium 1 minus X minus Y arsenide. This is quaternary. And similarly, we can also have indium 1 minus X, gallium X, arsenide Y, and phosphorus 1 minus Y. So these are the ternary compounds. These two are these are the quaternary compounds, and these are the ternary compounds. Now, if we plot, do a plot between band gap energies, Bg in electron volts, and lattice parameter, which is in Armstrong. So you will see that the gallium arsenide is mainly done. If you say this is 0 and this is 4, this is 2, 3, 1, and this is say 5.5, and this is a 6.5. This is how it is. So the gallium arsenide will be formed here. And then you will have above it aluminum phosphide, then aluminum arsenide, then sorry, this is not gallium phosphide. This is gallium phosphide, and here it is gallium arsenide, there is indium arsenide and rubidium, antimonide, and we can have gallium, antimonide. Now these materials, let's take green. This is an indirect bandgap material, and this is also an indirect bandgap material. And we can there's also aluminum, antimonide. This is an indirect bandgap material. There's indium phosphide here. And these are all direct bandgap materials. So the indirect bandgap materials, they are at higher, this is indirect bandgap. So they are at higher bandgap compared to direct bandgap materials. Direct bandgap materials have comparatively lower bandgap associated with them. And this is where is germanium, direct, and this is where is silicon. The only difference is that only the elemental indirect bandgap materials are falling below the direct bandgap materials. Compound semiconductors having indirectness associated with them usually have a higher bandgap compared to the ones which are direct bandgap semiconductors. There are a few more observations which can be made based upon the diagram, like the lattice constants of gallium arsenide is 5.6532. Rather, need not go to that extent. It is around 5.6 Armstrong, which is quite similar to aluminum arsenide as well, but only difference is that this is an direct and this is an indirect bandgap. This is close to 5.6, so maybe this is 5.66 and this is 5.65. So due to this observation, what we can imply is that since they have similar lattice constants, so mixed crystal composition is possible. Forming aluminum X, gallium 1 minus X, and arsenide. And this will be grown in lattice matched on the gallium arsenide substrate. This will be grown and lattice matched on gallium arsenide substrates. So similarly, by looking into the diagram, we can see that there are other possible mixed crystal formation of quaternary alloys, like for example indium, gallium, aluminum arsenide. So since they have similar band gap, similar lattice match, lattice parameters, and also we have indium, gallium, cyanide, phosphide. They can be lattice matched to indium phosphide as a substrate. Now, as we have seen in our previous diagram, that some of the compounds have a little bit of indirectness associated with them. So, let us take, for example, if we take this material only. In this material, this is an indirect material. If we increase, if the composition of the mole fraction is greater than 4.3, now many physical parameters of these ternary compounds are determined by the parameters of constituent binaries. Like if we are mixing two different compounds, their constituent properties will mix, and let's say, and that actually depends upon a law that is called Descartes' law. It's a very common law in alloys. So let's try to understand what Descartes' law is. Say the lattice constant. Let's take this ternary compound, indium X, gallium 1 minus X, and arsenide. So the lattice constant A of this ternary compound will be equal to the mole fraction into lattice constant of indium arsenide plus 1 minus X into the lattice constant of into A into A of gallium arsenide. Right. So it's the X multiplied by the lattice constant of indium arsenide into 1 minus X lattice constant of gallium arsenide. So this will give the lattice constant of the total ternary compound. Similarly, if we have a ternary compound, say A 1 minus X into Bx and then Cy and D1 minus y. So this is the ternary compound. So any material parameter, talk about material parameter Q, which is a function of the mole fractions of X and Y of this quadrant compound, will be equal to into 1 minus x minus y t12 x plus y 1 minus y 1 minus x t14 y plus x t23 y into x 1 minus x plus y 1 minus y. So basically it's divided by. So this is the denominator. Let's try to understand the numerator. First is x into 1 minus x into 1 minus x. Here Tij is the material parameter for the ternary alloy formed. So here Tij is the material parameter for the ternary alloy formed. By the boundaries I and J. Now first of all it is x into 1 minus x into 1 minus y into tx. So here we are taking t12, that means we are considering the first two elements of the series. So next we move on to the second one, that means 1 and 4. So we are considering, so first we have considered these two elements E and B, so that's why it's x into 1 minus x into, now we consider into 1 minus y t12 tx, the remaining one, plus y into 1 minus y. Now we are considering these one, y into 1 minus y into 1 minus x t14, this one. So first of all initially this one, then this one, plus x into 2 3. Now we are considering these two middle. That's why it is 1 minus x for this one, for first and fourth, and x into 2 3 for second and third. That makes the denominator parameter q. So x into 1 minus x, in between we have 1 minus y. So this is the first term, plus we have, this is the second term. Let's write it once more so it becomes clear. So it's x into 1 minus x. Use a third bracket here. It's a different color also. It's x into 1 minus x. 1 minus y t12 x plus y t. Oh, I have made a mistake in my previous one, so please consider the previous one. So I actually missed this term here. It should be t plus y into t43 y. So this was mixed. So let's look into this. Firstly, plus y into t43 x so plus y into 1 minus y (1 minus x) t14y plus x into t23y divided by x into 1 minus x plus y into 1 minus y. So our material is, we once again write, it's a 1 minus x bx cy t 1 minus y. So this is 1, this is 2, this is 3, and this is 4. So as you have said, it's 1 into x minus x. So first we are considering 1 and 2. That's why it's 1 and 2. X into 1 minus x multiplied by the effect on it caused by the 2 and 3, 1 and 4. So it's this one. Sorry. So this is for the first one, x into 1 minus x. Now it's getting affected by t12, getting affected by 4 and 3. So we need to also consider their effect. So x into 1 minus x into 1 minus y t12 plus the effect of 4, 3. So this becomes the first part. Next we do the same thing for the opposite. We are just replacing the x and the y's here. So it is y into, so here it was initially x into 1 minus x into 1 minus x, now it's y into 1 minus y, the first term. Then we have multiplied by the effect of this into this, so that is taken care by 1 and 4 and 2 and 3. This is the numerator and it's divided by the denominator. So this is will give you the material parameter Q of the Q stands for the quaternary one, which is related to the mole fractions x and y. This is Weygard's law.